Welcome to springlib.
Okay, so for this question, the magnitude of the magnetic field due to wire 1 should be equal to the magnitude of magnetic field due to wire 2. So therefore, we have mu 0 I1 over 2 pi R1 is equal to mu 0 I2 over 2 pi R2. As you can tell, mu 0 over 2 pi can be cancelled out. So therefore, I1 over R1 is equal to I2 over R2. So if I2 is equal to I1 times R2 over R1. So we know I1 is 6 ampere, R2 is the distance between the wire 2 to point P, which is 0.50 meter. And R1 is the distance between the wire 1 to point P, which is 1.50 meter. So therefore, let's determine the I2. So the current at wire 2 can be equal to 6.00 ampere times 0.50 meter over 1.50 meter. And this will give us the magnitude of the current at wire 2 is about 2.00 ampere. And since the direction of the currents in wire 1 is into the page, that means the direction of the currents at wire 2 should be out of the page, or you can say out of page. Let's say out of the plane, since the question was used plane. Okay, so they say out of plane. And the next question was asking us the net magnetic field at point Q, which is equal to B1 minus B2. Okay, so we have mu 0 I1 over 2 pi R1 minus mu 0 I2 over 2 pi R2. So eventually we have mu 0 over 2 pi times I1 over R1 minus I2 over R2. So mu 0 is the permissive it's the permeability of the free space, which is 4 pi times 10 to the power negative 7 Tesla times meter per ampere. I1 is 6 ampere, R1, which is the distance between wire 1 to point Q, is 0.50 meter. And I2 is 2 ampere, and R2 is equal to 1.5 meter, which is the distance between wire 2 to point Q. So therefore, we can determine the net magnetic field at point Q, which is equal to 4 pi times 10 to the power of negative 7 Tesla times meter per ampere over 2 pi, and times I1, which is 2.00 ampere, over R1, which is 1.50 meter. I'm sorry, 0.5 meter. And minus I2 over R2, which is, this one should be 6, my bad. And we have 2.00 ampere over 1.50 meter. And this will give us the net magnetic field at point Q is about 2.13 times 10 to the power of negative 6 Tesla. And since we know that B1 is greater than B2 because it's closer, and also the current is larger, so therefore the direction of the net magnetic field on point Q should be the same as the direction of the B1, okay, which is the right side. And for question C, well, we know the net magnetic field at point S is equal to square root B1 squared plus B2 squared. So therefore, it's equal to mu0 over 2 pi times square root I1 over R1 squared plus I2 over R2 squared. So we know mu0, we know I1, R1, and R1 in this case, which is the distance between the wire 1 to the point S, which is 0.60 meter. And when I2 is 2 ampere, and R2 is the distance between wire 2 to point S, which is 0.80 meter. So we can determine the magnetic field at point S, which is equal to 4 pi times 10 to the power of -7 Tesla times meter per ampere over 2 pi. Then times the square root, which is 6.00 ampere over 0.60 meter to the power of 2 plus 2.00 ampere. Oops, sorry. Over 0.80 meter to the power of 2. And this will give us the magnetic field at point S is about 2.06 times 10 to the power of -6 Tesla.